So today we discuss force between two parallel currents, and previous class we discussed solenoid and toroid. Okay, to calculate the magnetic field. Okay, the inside there's the donut. Okay, there's a magnetic field outside the toroid. The magnetic field with a zero. Similar consideration like that. Okay, so we discuss the magnetism here. So today we discuss force between two parallel currents. That's very important. Force between two parallel currents means there is a two current, means two conductor actually. Suppose these two conductor are parallel, and that's the conductor A, that's the conductor B, current IA, both are in same direction, IB. So IA, this where IA produce a magnetic field, and suppose they choose a point here, and if IA produce a magnetic field at that point, which direction? So if you want to find the direction, suppose there is a circle, and that's the front, and the dotted line is behind. There's a center and current direction in that. Okay, now apply right hand thumb rule. So here that point, okay, so magnetic field is downward direction. Field is look like a downward direction, B, if current goes this direction, downward direction. Okay, and I goes in that direction, current. So there is a force. There is a force, and that force F, that is equal to IDL cross B. We know that. Okay, and direction of current and direction of DL both are in same. So IDL cross B, now we apply that. So that's the force. If DL, now that's the force. Okay, that's the force. Current in say this direction. Okay, current in that direction, that there is a force. So that's force IDL. So IDL. Okay, so that's the clockwise direction. So force is this direction, and that force FB due to A. Okay, due to where A. So A and B are the conductor, and current passing through that obviously conductor. Okay, that's the FBA. Okay, and now if FBA, consider that is I, the current direction here, in that direction IB. Okay, so DL, suppose we choose the length of conductor BL here. Okay, suppose we choose L, and you see that is a DF. Okay, so that is DL, a differential length obviously. So L, and there's a magnetic field B, ILB, if I consider only magnitude, and the B, this magnetic field created by the wire A, and that force FBA, that force is due to wire A. Okay, now that's a B, that is equal to, from we know that application of Biot-Savart Law, we borrowing the concept. So Biot-Savart Law is center of the circular conductor, and here there is a magnetic field, the center of the circular conductor, and calculate magnetic field at sidewise. Okay, not here. Okay, so that's the B, that is equal to mu 0 I, means the current is IA, due to that IA, conductor IA, by 2 pi, if the radius, suppose say that is radius with the R, and this also with the radius. Okay, the radius R. Now put here, So we get final expression I B L B replaced by mu naught I A by 2 pi R. So final expression we get mu naught L I A I B by 2 pi R. The force is B A. Okay, clear? Actually these force, okay, from calculating here I cross B, okay, that's the I cross B. So that's and that magnetic field here, this magnetic field is called like a external magnetic field. Okay, there's a magnetic field, external magnetic field, not magnetic field created by IB. There's a magnetic field created by IA, obviously where IA. Okay, now here same condition, IB also create a magnetic field at, so there is a create a calculated magnetic field at that point due to IB current. So here we draw a, suppose a circular path. Suppose that's a font, okay, and there's a center. Similar concept here. So B in that direction. Okay. So right hand thumb rule. Okay. Now here same current direction. So B, obviously both are in same direction. Here is a B. That's a B. And at that point here B, that is a is like that, is towards me. Okay, suppose a top point, if these two lines are parallel, so that's the B. So here if, so there is a force if A B. Okay, A means where B create a magnetic field due to calculate magnetic field at where A, or lies on the, that point lies on where A. Okay, that is IB, sorry, that is IA in that direction, obviously IA, that's the DL. Finally we get L cross B, and here B, that B actually create by this B. Suppose there no confusion, that is B of where A, B of where A. Okay, now here we get I A L, capital L, where of the length, both are the same length as where. So B of B, now find B of B, that is mu 0 I B by same radius. Okay, these are radius with the R, that is 2 pi R, gap between these two. Okay, that is B equal to, finally we get mu 0 I B by 2 pi R. So final expression we get mu naught I A I B times L by 2 pi R, that is F A B. You see that both are the magnitude be the same. These are these magnitude of the force be the same. Now that's important. If the force in that direction, so where is the force? Direction of force. So I cross B. So I cross B. So that means, okay, force in that direction. Force, this force A due to B. Okay, so towards each other. So this force is towards each other. Okay, each other. From apply right hand thumb rule here. So that's force equal DL, DL and B. I, DL are both in same direction. Okay, so that's why this force is towards each other, and the magnitude be the same. Okay, so the force here, the force on B where due to where A. Similar here, force on where A due to where B. Okay, if both current are same direction, so conclusion is that if both current are same direction. So there is a force and both force are towards each other. So means, so these were now slightly bending towards this. There is a bending towards it. Now finally this look like this. There is a bending. There is a bending. Okay, clear? How to calculate FAB and FBA? Now there is another important concept. If both current are in opposite direction, what will happen? Suppose if both current in opposite direction, suppose this current and this current. So say that IA and that's the IB, and obviously these two are parallel line. Okay, so you see that this IA and create a circular path. Suppose these are the behind and obviously okay, and obviously B in obviously these are the downward direction, downward. Okay, downward, and they should be like this. Okay, so right hand thumb rule. Now similar, the force is now the important. What is the force? Now the current direction is the direction. So if now B due to A, that is I L, they were length the same, cos B. And that I and L are in that direction, so IB. So I cos B. So see that is I cos B. Okay, so that's why the force is in that direction. FBA, outside, not inside. Now similar condition here, calculate force here due to where B. So draw a circular path, that's the center, and now the magnetic field direction here. Okay, so that magnetic field here in that direction, opposite direction. So okay, that's a downward direction, and obviously I in that direction, I in that direction. Okay, so I A in that direction, B is downward, that B is B of B, that is B of A actually, B of B downward. So I cross B, this is I cross B or L cross B both. Okay, so that means the force in that direction, that is a force AB. Okay, but there the magnitude be the same, but they are in opposite direction. So if AB or FBA, that is equal to mu naught L IA IB by, suppose radius is a gap is a radius, obviously that's the 2 pi r. The magnitude be the same, but direction are in opposite. So after that, when current passing through that wire, these two are in opposite direction. So these were now bending. These were bending this direction, these were now bending opposite direction. Here these cases towards each other, bends towards each other. For the means there then where bends each other is bending away from each other. Here is bending away from each other. Okay, because the force is opposite direction. Okay, clear? That's the main conclusion is that. Okay, that's the force between two parallel currents. Okay, now we discuss another concept is called a magnetic dipole moment. So heading magnetic dipole moment. Magnetic dipole moment. Discussion of the magnetic dipole moment, that we recall some concept, torque on current loop. That's very important. We borrow that concept and apply the magnetic dipole moment. Okay. Before that, we for discuss a torque on current loop. Discuss before magnetic dipole moment. We discuss torque on current loop. Actually, we discussed previous class, previous 2-3 class back, but here there is some recall here. Okay, magnetic dipole moment is very important. So here there is a north pole, that is the south pole. So magnetic field north to south direction B. Now here we place a loop. Okay. Suppose current in like in that direction. That's the direction of current. Okay. So now calculate the force. So if current in that direction, B is opposite direction, so I and B, they are in opposite direction, so there is an angle is 180 degree. So sine 180 be the 0. So there is a no force here. Here current in that direction, B in that direction. So I cross B, so force is upward. Here I in that direction, B also same direction, so cos 0, sorry, sine 0. Actually the force equal to I cross B, ideal cross B. Okay, if I and B are in same direction, so that is a cross product, means uh, the sine theta, sine 0 be the 0. So there is no force here. And here current in that direction, magnetic field in that direction, so that is I cross B, so that force is downward direction. Okay, so there is a force, so there is a rotation, that's a rotation here. So rotation created by the force is called torque. Rotation here. Now this rotation is now look like this. Uh, if rotation is present, there is a torque. Okay, so we get F, that is equal to I dl cross B. I suppose I dl cross B, that's the force. So here's the current I, and suppose the length, this length, suppose we choose this length be the A, and this length be the A, and that length be B. So current in that direction, obviously this path. So I dl here is A, and that is a B, and A is a length and B. So okay, so there is a cross product. Cross product means there is a 90-degree angle. So sine 90 be the 1. Okay, sine 90. So here sine 90 degree, sine 90 be the 1. So I A B, that's the force. So if there is a rotation, so there is a torque, the tau. So tau equal to here, that is a B cross F. So B cross F, we get B, F, and there is sign. So B, okay, B, suppose there is this direction is B and the force is upward, so that here is a 90 degree. So sin 90 be the 1. So B, F, and F we get I, A, B, sin 90 be the 1. Okay, so tau, that is equal to I, A, B times B. That is expression of tau taught, and we know that. And here AB, and you see that this shape is look like a rectangular. Okay, and that A times B, length times breadth, we get a area. Suppose now the tau I AB replaced by the area times B, area of rectangle, that is length into breadth AB, area. Okay, tau equal to IAB. Okay, now there is a force, so there is some rotation. There is a rotation, and rotation is now if that slightly change. After that, these were previously the where is look like this. Where is look like this. Okay. Now force is upward, that's a B, force is downward. Now slightly change. Okay, these rotation slightly change, and this is the upper. Now slightly change. Slightly change. Okay, side rotation here. Okay, so that obviously that B in that direction. Okay, B obviously in same direction. So there is a force, and current direction suppose the same. They change. That's the B, and there is slightly change. Okay, there is a slightly change here. That's the force. That's the force. Due to that, there is a changing. If there is a change, so now the angle is this angle, when the tau IAB, the tau, now this tau is modified at IAB. Previously there is the angle is theta, and the theta is 90 degree. The F and B, and now B and F, or R cross F. Okay, the same condition. R means the radius of that circular. Okay, also called the diameter. If there is radius half, that is a half, we get a total. So here now that the angle is changed. Okay, the force and the direction is small b. Now that angle is theta, change. Slightly there the angle is change now. So that's the sine theta here. Now there is a theta present, and this theta is not equal to 90 degree, any value other than 90 degree. Okay, and there is a now consider the n number of turns, and consider the current loop has n number of turns. So if there is a n number of turns here, there is a, obviously there is a single turn. Now consider there is a suppose imagine there is a n number of turns. Now that the torque tau I A B, that is a n, obviously n I A B sine theta. Now, okay, that's a modified torque here. And torques are rotate. Okay, torques actually means a rotating vector. Okay, so here now we jump that today's concept, the magnetic dipole moment. From that, Okay, it torques at to rotate the current carrying coil. See, that's the rotate of current carrying coil, and placed in a magnetic field. And these coil placed in a magnetic field. Suppose that is a north, here is a south. So that's the magnetic field north to south. That's obviously the external magnetic field. Okay, and there is the sense the coil behaves like a bar magnet. Okay, these coil behaves like a bar magnet placed in a magnetic field. This like a bar magnet, a current carrying coil, and is said to be the magnetic dipole. Okay, and that's a very important concept. This is a magnetic dipole. Okay, and that's the account the torque on a coil due to the magnetic field. We assign the magnetic dipole moment. If there is a dipole, so there is a dipole moment. Okay, the magnetic dipole generate to magnetic dipole moment, and that magnetic dipole moment is a vector. So magnetic dipole moment represent mu is a vector, and for like electric dipole moment P, dipole moment vector P. Okay, that's a mu that is equal to NIA, depending on number of turn of coil, current passing through the coil, and there's a area. Area means there's a cross sectional area of that coil. Okay, rectangular area. Okay, now see that NIA. Now this tau torque, okay, tau, that is NIA representing a mu replaced by the, and NIA replaced by the mu. Now the torque tau and NIA replaced by the mu B sine theta. And there is a mu b sine theta, so finally gets tau that is equal to mu cross b, that is a vector product. And now it just look like this. Suppose there is a, and the current in that direction. Suppose there is a I current in that direction. Okay, and external magnetic field placed here B, that's the external magnetic field. So there is a dipole moment, and dipole moment, suppose mu is downward direction. Now I call another conductor here. Okay, and the current direction is the opposite of like that. That's I. Okay, and there's a mu. Dipole moment upward. So here that's a very important concept. So there is an energy relation. So mu, okay, there's a dipole moment is a vector, and the B external magnetic field, that's the, not confused, that's the magnetic field not created by that wire or that wire, that's the external magnetic field. External magnetic field. Okay, so from, we know that's like a example of our electric field, that is a electric dipole moment P. Okay, that's a electrostatic dipole moment. Okay, and there's a tau torque that is equal to P cross E. Okay, similarly for magnetic dipole moment tau, that is a magnetic dipole moment mu cross B. That's for electric, that's for magnetic. Now there is a energy, similar consider, there is a energy U, the potential energy, obviously potential energy theta, for electric potential energy, that is minus P dot E. Okay, so similarly, so magnetic potential U theta, that is equal to potential energy, obviously, that is minus mu dot B. Okay, mu dot B. And here we see that this case, If mu is downward, B is upward, so there's an angle, the theta be that 180 degree. So u theta in that case, left side case, that is cos 180 degree. So cos 180 means that is a minus 1. So minus 1 means, so minus minus plus mu B. Okay, so plus 1. So here is the highest energy. Here is the highest energy or more energy. And right side case, that mu is upward, B obviously is upward. Okay, and this condition here, that theta is 0 degree, so cos 0 be the 1, so u theta, that is minus mu B, and minus mu B means there is a minus term, means the lowest, so that the lowest energy. Clear? So here the SI unit of magnetic dipole moment. Now we discuss SI unit of magnetic dipole moment. So here you see that mu equal to u by B from here or here, if you use any of those equation. So u means joule and B means Tesla. So joule per Tesla. Joules per Tesla, that's the magnetic dipole moment. Clear? That is similar of electric dipole moment. Clear? How to find that magnetic dipole moment from that with the help of the torque on a current loop. Okay. Here it will take some little more time. So this lecture is too long here. It takes very small time. So there is a work done. There is a energy means there is a work done. So suppose if a work done concept is very important here. This energy obviously related to that the work. If a applied torque is external agent, if an applied torque at external agent rotates the magnetic dipole, okay, the magnetic dipole from initial orientation to final orientation, from and choose that is theta I to final orientation theta F, theta I to theta F. So the work done associated to like that, work done, the change in energy, so final energy minus initial energy, that's the work done. So work done by work done on the dipole, that's the this work done on the dipole, work done on the dipole by the applied torque, the applied torque, if the dipole is stationary before and after changing the orientation. Okay, if so there is a if dipole is stationary, okay, before and after changing the orientation, before orientation. Okay, and so we have identified that the current carrying coil, so final conclusion is that, the final verdict is that we have identified only a current carrying coil and a permanent magnet. These two important, current carrying coil and a permanent magnet. Current carrying coil and permanent magnet, these two, okay, have a magnetic moment. Magnetic moment. moment. A rotating sphere of change, also a magnetic dipole. Like a rotating sphere, also that and rotating sphere of change is also a magnetic dipole. Is also magnetic dipole. Like a earth, subatomic particle. So like that is a small bar magnet. Okay, there's a magnetic dipole moment is 5 joule per Tesla, and Earth also have a permanent dipole moment like that. Earth have huge 8 into 10 to the power 22 joule per Tesla, and like a proton also have electric permanent dipole moment. This is a magnetic dipole moment. Okay, 1.4 into 10 to the power minus 26 joule per Tesla. Electron also have 9.3 into 10 to the power minus 24 joule per Tesla. Okay, that's the concept. Okay. So let us to summary the today's class. A magnetic dipole moment. Before that, we discuss a magnetic dipole moment. We discuss the torque on a current loop, and here for discussion, here we jump from torque on current loop. There is a slightly bending, and we get a magnetic dipole moment mu. Okay, and there is a basic calculation, energy calculation, and what is the potential energy related to the work done, and there is some conclusion. And before that, we discuss force between two parallel currents, means two parallel conducting wire actually. Okay, so their conclusion is that if both current in same direction, so force is towards each other. After that, there is a bending this wire towards each other, close to each other, and if the both current are in opposite direction, so force are in opposite direction. So that is a wire is bending away from each other. Okay, like a bulging type. Okay, so today in the class here, if any doubt, always ask in comment section. I will try to give the answer. Next class we discuss new concept, new topic. Thank you.